Welcome to ECGR 4101, 5101. Today I'm very sad. Second to last class. The quiz didn't go well. Did I say this was lecture 24? Great. Today's embedded system of the day. What is it?
SumoBot.
It is a SumoBot.
It's a bot.
So a SumoBot, and there are many organizations that will make these. This is, the light doesn't work too well on this one. Let's see if I can fix that up. Nope. So with a SumoBot, you have a vehicle that has these nice wheels. Behind the wheel is a servo. Got lots of batteries. Interesting here, this is a light transmitter detector. It's used primarily to shine a light down on the plane surface, which is typically black with white edges, to make a ring. And the whole idea with the ring is you stay in the court or in the playing field. It's about maybe 3.5 feet white around it, and this keeps you from going outside of the ring, because the whole idea is you want to use this wonderful cow catcher in front to push your opponent out. And how do you detect where your opponent is? Well, usually you have these light transmitters, detectors as well, typically infrared, and oh, by the way, then you have this this cool speaker on the top to be able to psych out your opponents. All right. The important thing to note on this, by the way, these come as kits. Notice that it doesn't have anything wonderful like a some other type of transmitter receiver pair like ultrasound. But one thing that I wanted to point out on this, oh man, this thing goes like forever, is the actual board that this is. And in particular, oh come on. You can buy these cheap kits, which are a product from Parallax, and it is a, what's the device called? A Parallax basic stamp. And the basic stamp comes with a small little processor on it. It has a little bit of memory. That's what I was looking for. And the alternative is, when I went to the Microsoft Embedded Developers Conference, as a little freebie, they provided a kit. They took this board and they put a, ooh, look at that, a .NET micro framework chip, and kind of attach it some freaky way. I don't know what this, why it's all the different things. But it is an ARM7 core. Does anybody know what an ARM7 microcontroller is? Is that yes or no? Anybody ever heard the word ARM?
Yes.
Other than, you know, this?
Yes.
Okay, here. Other than this, all right? An ARM. This is one of the more interesting aspects of this. An organization came up with a design for a microprocessor, and they did it in software, in design tools, etc. They never ever built a piece of silicon. Then they went off and they sold this microprocessor core to various assorted people. For example, when I worked for Ericsson, we used a ARM-based microprocessor manufactured by Qualcomm for our cell phones. And so what they did is, Qualcomm bought this microprocessor core. They built all sorts of stuff around it, like the analog input-output, maybe, and they added a digital signal processor for handling the audio, and they attached radio interfaces. And what ARM did is they said, we will sell you this microprocessor core, in other words, the designs for this microprocessor, you build it yourself in your own silicon, and for every one that you build, we get a royalty of, I don't know, $1, let's say. I don't know exactly how much it is. And you think about that, that's pretty good, because most cases, you want to take a microprocessor and put other stuff around it into one piece of silicon, package it up, and sell it. And so this company has made lots and lots and lots of money never actually building their own silicon. They sell it off to TI. They sell it off to Qualcomm. They sell it off to, I'm trying to think some of the other companies that do it.
Samsung.
Who?
Samsung.
Oh, Samsung. I'm trying to think of the other ones I've actually seen. I think just about every silicon manufacturer around has actually bought this core and made a product with it as its base. You know, TI has their own MSP 430, but they also have processors that use the ARM core. And I think this one was done by, I'm not sure who this one was done by. I could look at the chip. Or not, because I can't really see it, it's too small. Actually, they put a nice big label over it, so I can't see what it was. So as a part of this contest, I actually wrote code using Microsoft .NET Framework, embedded tools. We downloaded our sumo wrestling code to this, and somewhere on YouTube is my contest where I actually run the thing, and I got second place. Yay. Out of 64, so that wasn't bad. The guy who beat me cheated, so that's all right.
It's always that way.
It's always that way, actually. And which means he cheated the whole way, and everybody was kind of pissed with him because you were supposed to have put a you're supposed to boot and then do a 3-second beep, 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 go. And what these guys did is they started the booting of the processor and did the audible beep first, or at the same time. And that was not in support of the rules. So they let him win anyhow, but that's all right, because second prize was a lot better than first prize. So. All right, so that is today's app of the day. So today's lecture of the day is going to be an introduction to operating systems. And for that, I have some available notes that I would love for you to take a look at, and these will be available. And I'm going to go through this fast. I'm going to go through a quick part of it fast and then show an example that will help you for your homework. And that is sharing the processor, a survey of supporting concurrency. And this is a general conversation. This is covered in chapter number 12 in your book. So if you were to say, what is important about embedded systems and operating systems, and how do you run operating systems? You've been writing your very simple operating system. Start this and run and do it forever. You know, the while one loop. But there are other things that you can do, and we're going to look at those today. And we've also talked about various methods of having processes do the right things at the right times. We've talked extensively about system requirements, right? And you've seen a lot of those as we've gone through. We've talked about complexity. I've talked about different types of things like threads. And then you have to worry about all of your resources. So let's take a look at, oh, by the way, and no shoe fits all, right? How many of you actually wear some of these shoes every day? I like to see the person wear this shoe every day, right? Everybody know what those are?
Waders.
Waders. Those of you who actually go to swampy areas and hunt will know what that is. All right, so RTOS, real-time operating system, is an interesting concept in that you can have a full-blown real-time operating system that does everything for you, and you can buy it off the shelf, or you could write your own, Or you can do something in between. So we need to take a look at how do you schedule tasks in the CPU, and what is better? How do we know when it's time to buy a real-time operating system, or if you want to write your own just simple while loop? And probably the full-blown up there would be something like a real-time Linux, where it's readily available, it's very complex, it might take a lot of space. There are other packages up there that you could buy too, like Green River, etc. So let's just take a look at some sort of definition. Let's say you're doing some oh, by the way, one thing that this also depends on is how many processors do you typically have in your embedded system? Low end. One, right? So when you have a single processor with a single core, you know, and I think everybody's familiar enough to say, you know, multi-core means you have dual or quad individual processors in one chip, right? So you have a chip with a single core. How many programs or how many lines of code are operating at or executing at any one time? One. So the whole idea is that when we're talking about an operating system, and we're talking about multiple execution of things going on, you can only run one thing at one time. So when we talked about interrupts, remember, you were running one thing, you had to stop, switch over and run something else, and once that completed, you go back and you continue to run that one thing. Same concept. So let's take a look. You're running another process. Every so often, you need to actually stop and say, a device called a scheduler will run, and will determine if I keep running my other process or I switch to something else. And why would you want to do that? Good reason. Remember that example I said earlier about a disk, right? And maybe the other process is, let's do something mundane. Sorting your entries in your phone book on a cell phone. I think I've talked about that before. Is that really important? No. And then something more important comes up, even though you don't have a disk on your cell phone. You might have something like a call request coming in. And so the scheduler would say, something else is coming in that's more important that must be addressed. And it will switch to that individual task or that interrupt service routine code. In this case, you're now relying on your scheduler, not interrupts, to be able to switch to interrupt service routines. But the whole concept of interrupts are still there. You'll be flagging that, hey, I've got something that needs to be done. So some of the things that are important is things like latency. How long between that little, see this little shock thing up here? This is when something says, I am an event that came up and I must run. And so the latency is the time needed to, or between when this interrupting type of activity says I need to run and when it actually does run. The response time is that amount of time in which it finally completes doing its task from when it said I need to run. Then there are, of course, the time associated with that individual task. And you also have to keep in mind that you have that scheduler that's actually taking up some of the time. Notice in each one of these bars, specifically the original task running, the scheduler, task or interrupt, the scheduler again, and then what was running before. Only one thing is running at a time because you have one processor. You could run one line of code at each time. So let's look at some of the options you have. You have something here called a round robin or a super loop. Really simple, no interrupts. In other words, you're coming close to what you've done already. This is pretty similar to what you are while one. Is this ready? Do it. All right, is this ready? Do it. Is this ready? Do it. So let's take a look. Each device always gets time to run, right? You're always assured of everybody being fair. Would you agree with that? We have nothing called starvation. Everybody gets a chance to run. Now, what's some of the so that's one of the advantages. Everybody is guaranteed to run. Question? Oh, what is one of the downsides or cons or problems with this?
The way I see it is if device A is ready, but device B isn't yet ready, and then it's got to go through the whole loop again, and if device A is ready before device B, device A will start back up, and only then device B will run.
So you're fair, but that's fair. Doesn't that count?
Yeah, but you're but it's still like a whole cycle delay.
Yeah. You have a whole cycle delay. Even if it's pretty important, it's got to go all the way through again. All right? What's another disadvantage?
No priority.
There's no priority whatsoever. Everything has the same priority. So then, in general, what's the disadvantage of that?
Everybody has to will have to wait for.
All right? Everybody has to wait, and you might lose data, right? So again, in this case, if this were a cell phone, and device A is the situation where you're actually sorting your address book, and it won't answer a call until you're done sorting the address book. Well, if a call comes in, that's your device B. Oh well, you missed the call because it was more important for you to sort the address book. So that's some of the difficulty with that. So there's a possibility also if one of these devices take an extremely long time to run, that there will be a big delay. Remember some of those definitions we did earlier? There will be a big latency and a big response time to actually get to something that may be important. So as an example of a round-robin application, let's say we have a digital multimeter that is based on some sort of microcontroller concept. So, so you have a case, all right? When the switch of the position of this says it's ohms, then you're going to execute some code that will configure the ADC. It will enable the ohms indicator. You'll do the conversion. You'll then format it and display the results at the end. Now, you look at this, that's not such a big problem, is it? All right? Because really, this switch has only, well, it has one, oops, get that back up there. It has 1, 2, 3, 4, 5, 6, 7, 8 positions, and you have one block of code for each one of those. And you're really only wanting to execute one at a time. That would be a good use of that methodology, because you're only running one at a time, right? And so actually this is a really easy application. Would you agree? Because it's pretty methodical. You really don't want to display the results before you've configured it for the specific button, enable the indicators, do the conversion, in other words, read the inputs, do the formatting for printing. So this is really a pretty sequential type of application. However, let's take a look at a network video phone, where you say, yeah, video and audio are processed in chunks. So every 33 milliseconds, you need to take care of each one of these. So WCET is, what do you think that stands for? And it's the time that you're spending on all of these things, all right? And how frequently do you need to do it? Well, you have to do it once every 33.3 milliseconds, and for audio, you have to do it once every 20 milliseconds. So the expectation is that you're going to send something and then receive something with once every 33 milliseconds. So let's take it. Let's take an idea, or let's look at how long all this takes. This is where I need this. So let's add this up. How much time is this? Let's see, 1 millisecond. That's 28 milliseconds. That's 28.1, 28.2, 30.9, and 31.9. So our video is going to take 31.9. All right? Now look at this. These are all short, right? You add all these up, it's, I'm going to guess it's somewhere around in fact, it's going to be easy. It's 0.323 milliseconds.
Four.
Oh, I can't add. 1, 2, 3, 4. All right. And you could all read that really good, right?
Absolutely.
0.324. 0.324 milliseconds. So if you add that up, hey, this should, no problem doing everything in 33 milliseconds, right? Oh, except there's a little problem here, right? You do this once every 33 milliseconds, you do this once every 20 milliseconds. So really you're doing this 1.5 times for every time you do this once. Right? Or you're doing this 3 times for every time you do this about 2 times. But here's the other problem. If we were to do the super loop, well look, this takes 27 milliseconds to compress. So if you did this, then this, then this, then this, then this, then this, and then you got to this, well, look at this. If you're supposed to do this every 20 milliseconds, you've just taken 27 milliseconds just for compressing. So you've missed 2 cycles. You will always lose data because in this methodology, wouldn't it be nice if you said, oh, whenever this has to be done, let's stop whatever we're doing in the video processing, handle the audio for the short little 0.3 milliseconds, and then we could return back to the video processing. Wouldn't that be reasonable? But with our methodology, which we said is a simple round-robin super loop, no interrupts. The thing is, you don't have a problem with sharing data because everybody does everything lockstep, one at a time. So the big problem is your tasks have deadlines. And because you don't allow interrupts, you won't be able to do that. So maybe we need a different thing. Maybe we need to allow something like an interrupt. Because again, as we said, the data comes in, the audio data comes in, it takes a small amount of time. It would be really nice if you were allowed to interrupt all of that. So the limitation is multi-rate systems. In other words, when there's several things that have to be done with different rates, it doesn't work well. So in this case of the voice and audio recorder, or the video and audio, you have a different frequency between the two. And you could potentially have very long response times, such that the maximum response time is going to be a summation of all of the tasks. And anytime you add a new device, it'll affect the timing of the other ones. So this doesn't work out too well. So maybe we need to do something with event triggering. So let's take a look at a very basic architecture for this. This means that you only do an activity whenever there's an interrupt. And in the end, let's see if we have a picture of this. We have a single while loop which says sleep. And that's all it does. And I see Mr. Wolf back there kind of snickering and saying, oh, sleep, yeah, I'd like to do that too, right? It doesn't everybody. So, no, in this case, what you rely on is any time an interrupt occurs.
That.
And I could swear I shut the sound off on this thing. anytime you have a,
That was your interrupt.
pardon me?
That was your interrupt.
That was my interrupt, but you know what? I masked interrupts. So I didn't service that interrupt. So where was I? Oh yes, back here. Event triggering using interrupts. Maybe I did kind of get interrupted, all right? This is very basic because the expectation is that anytime something happens, you will stop whatever you're currently doing, which in this case is sleeping. Sleeping, everybody know what that means for a microcontroller, right? You go into a very low power mode, and the only way to wake up from that low power mode is to get interrupted. So in that case, what will cause it to happen? We have this device here that will count every time the wheel rotates on your bike. Because what you want to know is, you want to know how far you've ridden, right? It's an odometer. And with this interrupt, well, that will be the wheel location, will kind of wake this up every time it goes past. In other words, it's like an event counter. And then you have this other stuff going on, like if you start pressing buttons so you can change the mode and set the times and stuff like that. And then, of course, you have a clock, and every so often, the timer will run for a certain amount of time and then wake you up and say, okay, it's time to advance the clock by 100 milliseconds, or whatever it is for your device. And then your only output, of course, is the LCD associated with this. Very low power. So the only code that you really need is set up some initial work, go to sleep, and then whenever the wheel rotation interrupt occurs, then you increment it, and if it says your rotation per mile needs to be adjusted, then you can adjust that. You could recompute what your speed is, change some stuff, and then maybe go ahead and display that on your screen. Same thing, if you're pressing a button for the mode, then you set something else, display, and it goes back to sleep. Or if the time of day timer says that it's time to increment, well, then you increment whatever the time is and then refresh the LCD with all this information. Oh, by the way, it may turn out that you may store this information, like the speed. You may store this for the mode, and the only time you really update the LCD screen is whenever the current time tells you it's time to refresh. Oh, hold it. Here's another one. So you have two counters here. One that increments the current time of day, one that says, I allow a certain amount of time until I refresh the screen. Saves a lot of computing power. And so if it's time to refresh the screen, then you do your computation and display your screen. But one of the problems with this is that you need to have some sort of periodic event triggered, let's say a timer. And there are a limited number of timers on your MCU. How many are allowed on the Renesas microcontroller?
5, 4,
I hear 5, I hear what?
4,
4? Which is it, 4 or 5?
4, 4.
You said 5, what's the fifth one?
It's like time 0 to time of
Well, that might be a good test question. How many timers in our processor?
4 timers and then compare match timers.
Say that again?
4 timers, 4 8-bit timers, and then we have compare match timers.
What's the last one?
The compare match timers.
Ah, okay. So I guess we do have 5, right? So, that's not very many, is it? And in fact, if you think about it, you really only have 2 16-bit timers, because if you want to measure anything for a certain length of time, you need to put 2 of them right next to each other, right? So you have a lot of limited number. And oh, by the way, you need to go to sleep after you've done all your work. So you need to ensure that you don't do much in your main loop. The interesting thing is that all code is in the ISRs. That makes your ISRs long. Typically, long ISRs imply better chance of having problems. So maybe doing something like a round robin with interrupt would make sense. In this case, for example, we have a very important device, like maybe handle device A. We will go actually there and say, I need something to do, and then that way you can set a priority. This allows you to have what's called foreground and background tasks. So you can have more than one priority level depending on which one you finish first or what you allow to finish before the other. I'm going to show an example of this. So remember the scheduling problem with our video audio example? Well, let's say if you had a different interrupt for handling your microphone and a different interrupt for handling your video. And so what you can do is you can ensure that whenever you had to read the audio data, you would allow it to be interrupted. So if it were in the middle of your compressing the frame for the audio, for the video, at least you'll be able to read that data from the audio. One problem of round robin with interrupts is that all tasks have the same priority. Even though there's a difference in priority between interrupts and the regular code that's running. So if you were to look at this, notice that this is at the same priority as this. Although in this case, at least you get to copy the contents of the microphone buffer so that you don't lose that data. The other problem you could have now is something called shared data, which I'm going to talk in a little bit more detail in our next class. In other words, if you have multiple pieces of code running that might touch the same data, you might have problems with where that data or how accurate that data is. That's a problem that we're going to talk in our next class. So, what I want to do is I'm going to switch to another set of notes because this is something that you probably have an interest of seeing because we have a problem associated with this. So if we look at, in a little bit more detail, the round-robin non-preemptive schedule, we've already seen a little bit of what is scheduling, and so let's look at the basis of round-robin. I'm not going to go into the code, but at the very least you should know how it runs. So, you've seen reactive systems where activities are processed based on interrupts that pop up every so often. Well, what happens if one of those interrupts is a timer? And one of those timers says, all right, every 1 millisecond, one task will run. Every 2 milliseconds, another task will run. Every 5 milliseconds, another task will run. And you need to schedule all those. And they're not really based on interrupts, but there's some things that happen periodically. So let's look at some of the rules. We're going to define our certain functions to be tasks. Tasks that need to be operated every so often. But here's another rule that's rather interesting, and that is you must finish a task before you can start a new one. So again, now in this case, for round robin, you're not allowing to interrupt. But at least we're scheduling it such that some of them may have priority. We'll see exactly in what situation. By the way, if there's more than one task to start, you start with the highest priority one. And by the way, if there is a task ready to run, run it. So let's take a look at an example. We have a couple of variables that we need to store that will change and some that will never change. So, here we have 3 tasks, 1, 2, and 3. They have a priority, and by the way, the higher priority, it'll run first. So priority 1, will run first if the time to handle it is at the same time. Oh, by the way, it takes 2 time sequences to run. Now here I'm showing elapsed time from 0 to 1 to 2 to 3. We don't know how much that is. Could be millisecond, could be a microsecond. It's just some time. Just keep that in mind. How often does task number 1 happen? Well, it could happen every 20 time sequences. Let's call all these milliseconds so you can get a flavor of this. So what we're going to say is that we'll start running, and every 5 milliseconds, task 3 will run, or will be scheduled to run. Every 10 milliseconds, task 2 will be scheduled to run, and then every 20 milliseconds, task 1 will be scheduled to run. And by the way, if task 2 and 1 are scheduled to run at the exact same time, who's going to run first? 1. I'm sorry, task 2. The one with the number 1 priority. All right? So, what we do is that when we start our round-robin scheduler, we will start with this variable called time for each one of these tasks. So the time of task 3, this is the amount of time that it will be until you schedule the next one. So after 1, 2, 3, 4, 5, this will be decremented to 0. That means that I will schedule this to run. And oh, by the way, once this decrements to 0, I reset this number to whatever its frequency is. Well, here's here's the time variable for number 2. Its frequency is 10 milliseconds, let's say. So I'll decrement 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. At this point right here, it goes from 1 to 0. It says, okay, it's time to schedule this. So I will schedule task number 2. And oh, by the way, at the same time, this decrements from 1 to 0. I will schedule task number 3. And then I reset these variables to whatever the frequency is. And as you can tell, task number 1 has a frequency of 20. So at the 20th time, it will actually schedule. And lo and behold, these all schedule at the exact same time. Now, since I say my length of time, in other words, how long does that task take to run, I can't run 2 things at the same time. So round robin says I need to do the highest priority one first. Right down here, this was the only one scheduled, so I will run it. And oh, by the way, it only takes 1 time sequence, and boy, there's not very much going on in this time, right? But here at 10 milliseconds after I started my round-robin operating system, I schedule task 2 and task 3. Who has the priority? Task 2. And so I will start to run task 2. It takes 2 milliseconds to complete. And after that, then task number 3 will run. Then what I have is at 15, I will have task number 3 scheduled. But here down at 20, I have the perfect storm where task 1, task 2, and task 3 will all be scheduled. Task 2 has priority, it'll run, then task 1, then task 3. And lo and behold, only 2 milliseconds pass between when I run it this time and run it this time. Again, this all happens because you only have so much time. So does this make sense? Now, what happens if I add another task? Priority 0. So that means it has priority over everybody else, and its frequency is 3. So it has to run every 3 milliseconds. So if I look at this, oh, here it is, it's scheduled here, and oh, by the way, it's got first priority, it's the first one to run. It's scheduled here again, runs right away, no problem. And then, at this point, this is where we get it rather interesting. We have both of these scheduled at the same time. So, we take the higher priority one, number 1. Then, at this point in time, number 4 is scheduled, but task 3 was waiting to execute. Task 4 is higher priority, so we execute task 4. Then we get around to task 3. And then, at this point, task 4 and 3 are scheduled at the same time. So again, we run task number 4 first. And then at this time, oh, look at this. We schedule task 1, 2, and 3 at the same time, and oh, then we schedule task 4. So we run task 4 at this time and schedule, then we run task 1, and oh, here it is. Task number 4 is scheduled to run again, so that has higher priority. And the big problem is, then we get to this point, and this one is scheduled again. What did we miss? This whole time passed and we weren't able to execute task number 3. So this is a highly loaded system. Loaded in the sense of, not that it drank a lot, but it, and nobody's laughing at my jokes. Nobody wants an A, jeez. That there's a lot of stuff going on, such that you're going to start to miss some of these tasks. And it gets even worse if you then say something like, oh, this task really takes 2 milliseconds to execute. In this case, this is an overextended system. Notice you have absolutely no blank time in here. You're running at 100% utilization. And how many times are we actually running T3? Well, it should have run here. 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 And it should have run here. So in this amount of time, it should have run, oh, and also here. Should have run 1, 2, 3, 4, 5 times, and it ran 1, 2, 3 times. So it's starting to miss an awful lot. And oh, by the way, are there other ones that are missing? Well, I think we're missing a couple of T2s here, aren't we?
I only see 1, 2, 1.
Now, we haven't missed any yet, but it's getting close. But notice, T4 is pretty much taking control of the whole system the entire time. So what does that, from the respect of an embedded system, what does that look like you need to do?
Make it more efficient.
Say that louder.
Make it more efficient.
Make which one more efficient?
T4.
Make T4 more efficient. What's another option?
Go for an OS with a go for an OS with a decent scheduler.
Go for an OS that does what?
A decent scheduler.
Oh, a decent scheduler. But you're still 100% utilization, right? So what's the resource here that's being used up totally?
Hours. Get a new processor then.
Clock cycles. So you need a faster processor that will run everything a lot faster, right? Or maybe another processor, and you have a dual core, one that handles one thing, one that handles another. That's why in the cell phones you often have different processors for the digital signal processing and one for the baseband, the regular digital aspect, your sorting of the phone books and stuff like that. So we'll continue on operating systems number 2 in our next class. Thank you very much.